All right, so one of the things that you know Aristarchus argues, and it turns out that Aristotle also knew about this possibility, is the following, and this is what's called parallax. Okay, this is extremely important in astronomy. All right, so parallax is a way that we measure the distance to things when they're extremely far away. All right, so here we go. Okay, so when the Earth is on one side of the sun, if you observed a star, then if the stars are different distances from each other, and of course they are, that star would appear, you know, against some background of stars, right? From this angle, let's say this. I guess this is July. From this angle, the stars, the background stars would, you would notice that the star is lined up with this particular grouping of background stars, and then 6 months later, it's January. And by the way, this is called the baseline when you observe objects. But by the way, that this idea of parallax is used all the time. Here, let me finish this part. So 6 months later, you look at that star, and remember, this is a little bit closer to Earth than some background stars. But notice that star, this star has now shifted. So it's this little asterisk-looking thing. Has shifted with respect to the background stars, right? So and it would be an incredibly small shift. That small shift is what's called a parallax. All right. Let me go back just a couple of slides. So this is another way of measuring parallax. When we actually. That's not a good picture. Sorry. Geez, I didn't mean to go that far. So anyhow, you measure the baseline. So if you know what the baseline is, if you knew the distance between the Earth and the Sun, which of course in more modern times we knew that distance very well, you could measure this. You could measure the distance to stars. Now here's the problem. Okay, so remember, you're talking about 2,500 years ago for Aristarchus, and roughly the same, a little bit less time to Aristotle. The thing is, the stars we now know, are tremendously distant from each other. For example, between the sun and the nearest star, it takes light, which is the fastest moving thing in the universe. It takes light more than 4 years to cross the distance. And that's just the nearest star, right? That's just the nearest one that we have to our sun. All right, with that in mind, it's not surprising that Aristarchus proposed this, and later on, Aristotle comes along and he says, he's like, no, there's no way that the Earth goes around the sun. I mean, if that were the case, then we would notice, the nearby stars shifting because of this phenomena of parallax. And because I don't see that, which, by the way, is a completely scientific reasoning, because I don't, remember, this is Aristotle living about 100 years after Aristarchus. Because I don't see the parallax, then he made this grand conclusion that the Earth does not go around the sun. He concluded that the sun was the thing that goes around the Earth. And unfortunately, Aristotle was extremely influential, and Aristarchus was, again, he was a name that was almost lost in history. But Aristotle was read throughout the ages by humans, and it kind of got us stuck in this idea that the Earth was the center of the solar system for a long time. Of course, now let me fast forward. With the invention of the telescope, and then you needed another 200 years, right? So we're talking about 400 years ago, humans invent the telescope, we turn it to the sky, and then about 200 years after that, the telescopes are so advanced that you're able to see. I think it was right around 1800 that the very first parallaxes were actually measured, because the stars are so incredibly far away. Nowadays, we have telescopes that can measure this very, very accurately. We even have a spacecraft that can measure the parallax. We're not restricted to the baseline of the Earth-Sun distance. There's spacecraft out there. There's one in particular called Gaia that extends the baseline so that we can accurately measure, using this method of parallax, the distance to stars, because that's extremely important to astronomy, knowing that number very, very well. All right, now we come to these things have any of these with mathematical examples. I'm going to do this. I'll try to do this actually towards the end of this of Chapter 2 series. Okay, so I will give you the example of Aristophanes. All right, so Aristophanes comes along, and he was he was the next person to by his time, Aristotle had lived and had established himself. But what Aristophanes did, he lived in Egypt, which was he's considered Greek, even though he lived in Egypt. He had he followed the Greek culture and things like that. I mean, the people of his time were, even though living in living in Egypt, he did follow a lot of the Greek culture. At any rate, that part doesn't matter. He was the chief librarian of the great library of Alexandria in Egypt. Okay, so this was a very famous library that was eventually burnt down. Actually, most of the books were destroyed. But at any rate, during his time, this was the place where most of human knowledge, going back maybe even 1,000 years from his time, was stored. And he was going across these papyrus rolls, these rolls where they used these papyrus to make paper, and he saw something, and he made this observation. Again, this was just a book that he found in the library. All right, so I want everybody to understand that he finds this book, and the book says something interesting. It says that somewhere to the south there is this place called Syene, and it actually it doesn't exist anymore, but it was a place along the Nile River in Egypt. It was about 800 kilometers. It turns out it was about 800 kilometers from Alexandria. All right, remember, Alexandria is up towards the Mediterranean, and so he reads in this book that that on a certain day, and it's a very specific day, June 21st, the first day of summer in the northern hemisphere. On that particular day, a well in Syene, all right, so a well that's dug straight down into the earth. there was no shadow. The rays of sunlight would go straight down the well. And he was like, okay, that's an interesting fact. And so what he does, and this is extremely scientific, on that same day, he measures the angle of a shadow at it was at noon, by the way. It's right at noon. When noon is, of course, when the sun is the highest in the sky. So at noon on June 21st, again the first day of summer in the northern hemisphere, in Syene there's no shadow. In Alexandria, there's a shadow and he measures it to be 7 degrees. And he realizes that the sun is so far away. Again, they didn't know how far away it is, but it's so far away that the rays of light that arrive on the Earth are parallel to each other. And that's true. They're absolutely parallel. Now, the Greeks were really good mathematicians, especially with geometry, right? And so he realized that if the rays of light are parallel, and the one in Alexandria was coming in, and it cast a 7-degree shadow. That 7 degrees reflected. He fully believed that the Earth was round. I mean, that was pretty well established in the Greek mind at the time, and so if this 7 degrees was reflected by the angle between, like if you went from Alexandria to the center of the Earth, and then from the center of the Earth to Syene, that would be the angle. And so it turns out that angle, and I'll write this equation down. Okay, so that angle, which in turn turns out to be 7 degrees, divided by 360 degrees, which is the full angle of the circle, is equal to the distance between Alexandria and Syene divided by the circumference of the entire planet Earth. And so, again, Aristophanes is living in Alexandria. He knows about Syene, but he's never been there. He actually finds some guy. We don't even know who it was. That name, whoever it was, his name is lost to history. But he pays this guy, and I always imagine when I tell this story that he probably paid the guy half or less, maybe. But what this guy's job is to follow the Nile and walk all the way to Syene, counting his steps. He literally counts his steps, and then walk all the way back and get the rest of his money, right? So he walks this. I mean, that's a long way. 800 kilometers is not a minor distance, right? So he walks all that way and then walks all the way back, and probably took him, months and months and months to do this, but he does it. And and Aristophanes, waiting back in his cozy place of the place wherever he lived in Alexandria. He's just waiting there for this guy to come back, and the guy comes back with the count, and so he knows from the count. Aristophanes knows what the distance is. Once he knows the distance between Alexandria and Syene, again, it's roughly 800 kilometers. He was able to use his knowledge of geometry to measure, in a very primitive sense, but at least gave, for the very first time in human history, a size to the Earth. All right, and the value that he is very close to 40,000 kilometers, which is not very far off. I mean, it's not exact or anything like that. In today's standards, you'd be embarrassed to write that number in a textbook or something like that. But for more than 2,000 years ago, that was an amazing thing. It was an amazing feat to come up with that number. and yeah, so